Myself, Karanam Narayana Rao, Assistant Professor, Vijayanagara College, Hosapete. Now in this session we shall understand the Newton's rings. When a plano-convex lens of large radius of curvature is placed on a perfectly plane glass plate, then a thin film of variable thickness is formed between the surfaces. If the lens is illuminated by a monochromatic light, a series of alternate bright and dark rings are formed with the central dark spot. The rings get closer and closer as we move away from the center, and these rings are called as Newton's rings. The rings can also be seen in the case of a transmitted light as well. Consider a plano-convex lens placed on a plane glass plate G. Then a thin air film is enclosed between the two surfaces. When a ray of light MP is incident on the lens, a part of the light is reflected from the point P, and at the same time the remaining part is being reflected from the point Q at the upper surface of the glass plate. These two reflected rays produce the phenomenon of interference. So when the monochromatic light, which when being incident on a glass plate mounted at an angle 45 degree, then this ray of light is being incident on a plano-convex lens placed on a glass plate, and these rays of light, which when being reflected, produce the phenomenon of interference, produces an alternate bright and dark fringes which are being produced, and thereby it produces the concentric fringes which are called as Newton's rings. The thickness of the air film at the point of contact of the lens and the plate is 0, and it appears dark when observed by the reflected light. The thickness of the film increases as we move away from the center. If the concentric circles are drawn with the point of contact as the center, then the thickness of the air film of each concentric circle is uniform. Hence, a set of alternate bright and dark rings are being formed, which is being represented as shown in figure. So you are observing the concentric circles or the concentric rings which are being formed within the vicinity of this plano-convex lens. If T is the thickness of the air film and mu is the refractive index of the air and R is the angle of refraction, then what is this value of reflected rays? The reflected rays Pn and Qr. So whenever this monochromatic light, which when being incident, that is being incident at the point MP. Now whenever this ray of light, which when being incident, it is reflected from 2 points P and Q, and they are the two rays at these 2 points, the two reflected rays are being reflected. These two reflected rays are close and parallel to each other. As they are close and parallel to each other, they produce interference. As one of the rays reflected from optically denser medium undergoes a phase difference of pi, and the path difference is lambda by 2. Therefore, the path difference between the reflected rays is delta is equal to 2 mu t into cos r. For normal incidence, r is equal to 0, cos 0 is equal to 1, and mu is equal to 1 for air. Therefore, this path difference is 2t. As one of the rays reflected from optically denser medium suffers a phase difference of pi, having the path difference is lambda by 2. Therefore, the actual path difference is delta, that is equal to 2t minus lambda by 2. For the bright fringe, the path difference is given by 2t minus lambda by 2 is equal to n lambda, or 2t is equal to 2n plus 1 lambda by 2. Where n is equal to 0, 1, 2, 3, etc. For the dark fringe, the path difference is 2t minus lambda by 2 is equal to 2n plus 1 lambda by 2. On simplification, 2t is equal to n lambda, where n is equal to 0, 1, 2, 3, etc. Now from figure, AD into DB is equal to CD into DE. That is equal to CD into DE can be written as 2R minus CD. 2R into CD minus CD into CD is CD square. This from figure, AD into DB is equal to CD into DE. This DE can be written as 2R minus CD. AD is equal to DB is equal to D by 2, where D is the diameter of the ring and the value of higher orders of CD square may be neglected. For small values of CD, CD square can be neglected. Therefore, CD, that is AD into DB, is D by 2 into D by 2 is D square by 4. That is equal to 2R. CD is nothing but T. That is equal to 2RT is equal to D square by 4. Therefore, the diameter of the dark fringe is given by, for dark fringe, the path difference is n lambda. D square by 4R is equal to n lambda, or D square is equal to 4R into n lambda, or D is equal to square root of 4R into n lambda, or D is proportional to square root of n. Therefore, the diameter of the dark rings are proportional to square root of natural numbers. N is integer, which can take the values 1, 2, 3, etc. That is given by 1, 2, 3. They are natural numbers. For the bright fringe, D square by 4R is equal to 2n plus 1 lambda by 2, or D is equal to square root of 2R into 2n plus 1 lambda, or D is proportional to square root of 2n plus 1. The diameter of the bright fringes are proportional to square roots of natural odd numbers. Here, if n is equal to 0, it is given by 1. If n is equal to 1, it is given by 2 into 1 is 2. 2 plus 1 is 3. So it can be written as square root of 3. So 1, 3, 5, etc. which are said to be the natural odd numbers. And to find the width of the rings, consider the dark fringe. For the dark fringe, D is equal to 2 into square root of Rn lambda. If D1, D2, D3 are the diameters of first, second, third order of the rings, which are given by D1 is equal to 2 into square root of lambda r. D2 is equal to 2 times square root of 2 lambda r. D3 is equal to 2 times square root of 3 lambda r, and so on. Here n can take the values 1, 2, 3, etc. which are given by D1, D2, D3 and so on. The width between the first and second ring is given by square root of 2 minus root 1, that is equal to 0.4. The width between the second and third is proportional to square root of 3 minus root 2, that is equal to 0.3 and so on. Thus, the width of the rings decreases as the order of the rings increases. Now we shall find out an expression for the wavelength of a monochromatic light. Consider any two bright rings corresponding to m and nth orders. Then for mth bright fringe, the diameter is dm, that is given by dm square by 4r is equal to 2m plus 1 lambda by 2. For nth bright fringe, the diameter is dn, that is given by dn square by 4r is equal to 2n plus 1 lambda by 2. Now substituting these two values, dm square minus dn square by 4r is equal to m minus n into lambda, or lambda is equal to dm square minus dn square by 4r into m minus n, which is the formula with which we can calculate the value of the wavelength. Hence, the wavelength of the monochromatic light can be calculated using the relation lambda is equal to dm square minus dn square by 4r into m minus n. Thank you.